well, hopefully you did well on quiz 31 just a moment ago. As we start a new section in our notes as we build on this idea of sequences, we come to what's called a series. We tend to think of a series as something that drags on, so to speak, especially if you're a sports fan. Any baseball fans in here? Baseball fans. Okay, I'm a baseball fan. Today's opening day, so the Cardinals start their baseball season today. Basketball fans? Basketball fans, the NBA will play a series of games. So basically, here's the idea of a series, right? One game doesn't determine it all. You get up to 7 games against the opponent, and whoever wins the most, whatever the cumulative outcome of the series is, that's who advances or wins the championship. Does that make sense? It's kind of the total result of all of it. That's the idea of a series. You kind of put it all together. Well, if you think of that, it'll help you remember the definition of a series in math. It's the sum of the terms in a sequence. It is the sum of the terms in a sequence. So a sequence is the numbers themselves. The series is if you add them all together. Now, obviously, you couldn't use an infinite sequence because the sum would be infinity. Or if it was a decreasing sequence, obviously the sum would be negative infinity, right? So we would have to define limits there, but it's the sum of the terms, predefined terms in a sequence. We're going to use something in a series called summation notation. Okay, summation notation. Notation means the way something is written. Summation refers to adding. So it's a way we write that we are adding stuff, but we're not going to use a plus sign. Summation notation uses a Greek letter. It's the Greek letter capital sigma. Those who are in geometry already recognize this. It kind of looks a little bit kind of ish like a, I don't even know, a 3 kind of, but backwards, and kind of like an E maybe. Anyway, maybe draw it a little bit more perfectly there, try to do it a little bit better. But a sigma, okay, this is the summation notation. What we'll do with a series then is we will add certain terms of the series together. So what we're going to have is we'll have a starting number in the series and we'll have an ending number that could be plugged into the sequence as well. So we're limiting it. We're going to use the letter I for our value, and I will range from M, which will be our starting number, to N, which is our other number. M is what we refer to as the lower bound. The lower bound. A bound or boundary is the edge of something. Okay, it binds it together, it encloses it. The lower bound is the lowest number that gets plugged into the series. The lowest number that gets plugged into the series. N is called the upper bound. This would be the biggest number that you plug into the series. So it looks really mathy and really, if you're not sure what it is, frightening. It's really simple. This means add up all the numbers between M and N as you plug them in. So plug in from M all the way up to N into this particular series. We're going to have an algorithm, though, for our I values. We'll notate this A sub I. This is the algorithm for I, but in a series we call it the argument. The argument is another name for the algorithm that's being used in a series. And collectively, that's summation notation. Hinges on the Greek letter sigma, which indicates a sum. You're going to add things together. You're going to add together all the values that you get from your algorithm or your argument, where you're going to plug in all the values between M and N. Literally, let me show you what this means. You don't need to write this in your notes because it's a little wordy. It just takes up space. But literally, you're going to plug in A sub M. Then you're going to plug in A sub M plus 1. Then you're going to take A of M plus 2. And you're just going to keep getting bigger and bigger and bigger terms until eventually you get to A sub N. So you're going to be plugging in for the argument your values from M, and then bigger than M, bigger than that, bigger than that, bigger than that, until eventually you get to the N value. And then you stop. And you're going to add all the numbers together. Let me have you write a few examples in your notes. And I think after you've seen a few of these, you're going to have this series thing figured out. Let's take the summation or the series from 2 to 5 for the argument I plus 3. We'll take a really easy argument here, really easy algorithm, if you will. I plus 3. All right, what we're going to do is we're going to plug in values into this argument or into this algorithm starting with 2. So class, we're going to start with 2 plus 3, 5. Then we're going to plug in bigger than 2. That means 3. 3 plus 3, 6. Then we're going to take bigger than 3, which is 4. We're only doing integers, which is nice. By the way, that's the reason why the letter I is used, because we assume integers only. 4 plus 3, 7. And then notice we've reached our upper bound. 5 plus 3, 8. What we have done is we've plugged in all the numbers for I, all the integers for I from 2 to 5. We've plugged in 2, 3, 4, and 5. But the summation notation says we're going to add those values together. And when you add 5 plus 6 plus 7 plus 8, what do you end up getting? You can use a calculator if you need to. Abby doesn't need to. She got 26 and she's correct. That's how a summation works. It's like you've got a series, but you're adding the values in the series together. Write this example down. We'll step it up a notch. Let's take the series from 1 to 4 for the argument 3i squared plus 2. The series from 1 to 4 for 3i squared plus 2. This means the first number we plug in, class, is a 1. And we just plug it in for I. Well, if you square the 1 times 3 plus 2, now what do I plug in? 2. You square the 2 times 3 plus 2. Now we plug in 3. And we just keep plugging it in over and over again. 3 squared times 3 plus 2. 29 is correct. A little hesitancy there. All right, and then we plug in. Notice we've now hit our upper bound, so we're done. That's happy, right? Okay, we're going to plug in a 4. 4 squared times 3 plus 2. But again, since it is a series, class, it is the sum of the terms in the sequence. All right, so if this were a sub n equals 3n squared plus 2, I would have 5 comma 14 comma 29 comma 50. Since it's a 3i squared plus 2, and we're taking the series from 1 to 4, instead of just these 4 numbers being the 4 numbers of a sequence, we're going to find their sum. And what do we end up with here for our sum? 98. Questions on that? You get the idea what we're doing here? Write this one down. This one's, you're going to want your calculator probably. Let's take the series from 1 to 4. For 1 over I. Now, on the front end, this is easy. It's the back end that's annoying and you want your calculator. What's the first number that would be in a sequence if that's all we were doing? 1. Because you put 1 over 1. The next number is going to be 1/2 because you plug in a 2. The next number? 1/3 because you plug in a 3. The next number? 1/4 because you plug in a 4. And we're done because we stop at plugging in the 4. Make sense? But since it's a series, we add the values together. And this is where a calculator helps because we're too lazy to get a common denominator. 2 and 1/12 or 25/12, since I don't like mixed numbers, but 2 and a 12th is not wrong. I wouldn't take points off for that. Make sense? Write this one down. The series, that's a horrible sigma. That's still bad, but whatever. The series from 1 to 5 for 4i. 4 to the I, excuse me. The series from 1 to 5 for 4 to the I. When we plug in the 1, we get 4. Then we plug in a, and we get, all right, someone besides Audrey. Then we plug in a 3, and we get, all right, someone besides Brandon and Audrey. Then we plug in a 4, and we're thankful for our calculators. 256. And we get 256. Good. And then we plug in a 5, and we get 1024. And now we're really, really thankful for our calculators because we're going to add all those numbers together with our calculator. And what is the series from 1 to 5 for 4 to the I? 1,364. Look at my nose. Yep, that's what I had as well. All right, questions on this? Series seem pretty easy? Now, there's shortcuts. And over the next couple of lessons, we're going to look at shortcuts we can use to solve these fast. Because let's be honest, what if we had the series from 1 to 15? Oh, Yeah, or a series from 1 to 14. I mean, as the upper bound gets bigger, this just gets obnoxious. There's got to be a faster way, and there are faster ways for certain series specifically. So we're going to look at some shortcuts. What I want you to do for now is start a new page in your notes, a brand new sheet of paper in the notebook. Call it your formula sheet. We're going to have a lot of formulas. I say a lot. It's about 10 formulas in this section. About 10 formulas. So start a brand new sheet of paper in your notes. Call it your formula sheet. Maybe put that at the top of the paper, and you might want to use a sticky note to mark this, or some way mark this page so that way you can find it easily for studying. The first formula that I want you to put on the formula sheet is actually one we already know. I'll use the term formula loosely, but for a recursive sequence, I want you to remember that a sub n minus 1 equals previous term. It's not quite a formula, but it's close enough. I'm going to put it on the formula page because this is something I want you to study when you're studying your other formulas. So recursive sequence, a sub n minus 1 means previous term. That's not new, but it bears repeating. The next formula on your formula sheet is also one you already know. It's the formula for an arithmetic sequence. For an arithmetic sequence, a sub n equals a sub 1 plus the product of n minus 1 times d. Again, not new, but it bears repeating. Again, putting anything formula E on this page. The third one is new. And it's for what we call a constant series. A constant series. This one's really, really easy. Let me move this out of the way as I drop down further on the chalkboard here. Constant series is really, really easy. The formula looks maybe slightly annoying, but it's really not bad. It's the series as I goes from 1 to n for c, which is a constant. The series from 1 to n for c is simply equal to cn. The series from 1 to n for c is equal to cn. Let me give you an example you might want to put with this. What if I said the series as I goes from 1 to 9 for 5? Notice 5 is a constant, correct? There isn't an I in the argument. So if I plug in a 1, there's nowhere to plug it in. What do I get? 5. Then I plug in a 2. There's nowhere to plug it in. What do I get? 5. I plug in a 3. There's nowhere for it to go. What do I get? And I keep getting 5s up till I plug in the 9. Does that make sense? Which there's nowhere to plug it in, so I still get a 5. So in other words, I'm just going to get 5 9 different times. In other words, 5 times 9, the constant times the upper bound. So this is simply going to be, class, 45. That's the easiest series there could possibly be, is a constant series. It doesn't get easier than that. But a constant series, just multiply whatever the constant is by the upper bound, assuming we're starting at 1, and that's what we're going to assume for a little while here at least, is we're going to start at 1 for our lower bound. That's all there is to it. So if I had this series as I goes from 1 to 12 for negative 6, what would be the series from 1 to 12 for negative 6, class? Negative 72. You're just multiplying the constant times that, because that's literally what you would have if you worked it out. Negative 6 plus negative 6 plus negative 6 plus 12 different times. So negative 72. Questions on constant series. And I really wanted to get to the last thing, but I've got like 1 minute and I wouldn't have time to show it anyway. So we'll stop there. We'll stop there. Page 460 for homework. Page 460 for homework. Do numbers 1 through 6. And we get to consecutive integer series tomorrow, but didn't have time for that today. All right, page 460, numbers 1 through 6. We'll take a look at that, and then tomorrow I'll give you a few more series where we have formulas where we can quickly and easily calculate. That's a lot more fun than plugging in numbers over and over again and then using our calculator. All right, page 460, 1 through 6. We'll continue talking about series tomorrow. We'll take a look at the quiz tomorrow as well. Have a wonderful rest of your day, and when the bell rings, you will be dismissed.